Okay, yeah. So that is after you choose a that is regression. Of course, you'll see now this pop-up window. Okay, and it will require now you to input your Y range, X range, and if at all you've chosen if that is in your range, you've also that is selected the titles, then you will have to select that you've in your data, okay, or in your range, you've also included the labels, okay. So good. But in case maybe you've selected the data just from the only the values, okay, no need to do what? No need to choose the labels, okay. Then our confidence level, we will use that is 95% confidence. Remember, I had also said that we might have that is we have mostly most used three confidence levels. That is 99 confidence level, mostly for medical experiments. Okay, these are majorly for medical experiments, meaning that is you must have that statistical confidence. Okay, when it comes to medical experiments. Okay, so anything less than 99, of course, we can't say it will be that is statistically significant. Okay, then your model won't be reliable, and you might have maybe to recollect your data, or maybe to that is to choose your another independent variable. Okay. Then for the general research, we usually use 95% or 90%, but the standard one it's 95%. Okay, so of course we can decide to select that is the confidence interval. Then after that we have the output options. Okay, so output options I had shown you, that is if for example you want it to be in a new workbook, okay, or in a new worksheet, you'll just click that is okay. I will use this, okay. If you want it in a new workbook, meaning it will open a new Excel, okay. uh, Now you can also choose a new a new workbook, okay. But for my case, I can that is I can decide to use a new worksheet, meaning it will add another sheet here, okay, to do what? For the analysis, or paste our output there, okay. I can as well use that is the output range. So the output range is mostly if you want to get your output on the already existing worksheet, okay, or for on your current worksheet which you are using, okay. Then under residuals, okay, under residuals, I usually prefer to that is to select the that is residuals only, okay, to only select residuals only, okay. If you want standardized residuals, of course you can still do the same, because we know that is the standardized residuals, basically it's the observed, okay. It is basically maybe the formula for us for the standardized. Now they will take the observed, okay, the observed values minus the predicted variable, that is values, divide by estimated standard error, okay, standard error, okay. So basically this will give you that is standardized that is residuals, okay, when that is the back or the mathematical calculation of it, okay. Then if you want the residual plots, okay, that is if you want to see that is how that is the residuals will look like in a plot, okay, you can as well that is use that is residual plots. Okay. All right. So for my case, I'm interested now to go with the residuals. So I'll just click OK. Okay, I'm missing the output, so I need to select maybe my output here and then click OK. Okay. Once I click OK, you'll see now I have that is some outputs. Okay, that is the regression statistics. Okay, then after that you'll see we have ANOVA. Okay, we have ANOVA, and then we have now the coefficients. Okay, let me just undo and let someone in. Okay, so that is you'll see now the coefficients. Okay, and the standard error. Okay, you'll also see t statistics, lower, upper quartile, lower, all that. Okay, but our point of interest will be on the coefficients here. Okay, the point of that is of interest will be our coefficients here, the ANOVA parts, okay, also the residual parts, okay, so that you may see how that is these calculations have come up, and also this part, okay. Maybe if you want to learn more, you can just go and research about that is the t statistics. You can research about, of course, the p-value. We'll talk about the significance f here, okay, against the p-value, and then you can just go and study that is more on this part, okay. So but my point of interest here, because I'm dealing with a simple linear regression, it's on the coefficients, okay. So remember, we'll create a model like the one we did when we used what, when we used the line, that is the chart and trend line. Okay, you can see if you have that that is a presentation, or if you have that on your site, you can see these are the same values which you got. Maybe I can just redo it again, that is very quickly, so that we may compare very quickly. Very quickly, let me just do that very quickly. Okay, good. So for this one, we'll compare the that is the output here. We'll compare the output. Okay, good. Now let's go and explain what multiple R means, what is R squared, what is adjusted R, what is that is standard error. Okay, and also the observation. All right. Okay, good. Now let's start with multiple R. What did I say about multiple R? What did I say about multiple R? Someone? Someone, please.
I think multiple we use it when we have more than one dependent variable.
No, maybe
Independent variable, that is.
you are confusing it with the adjusted R.
More than one.
Mm-hmm. You are confusing it with adjusted R squared.
Okay, it is not with the more than one independent.
No, no, no. Multiple R.
Uh,
Is it goodness of fit? Kind
No,
of.
you are confusing it with R squared. Yes, Titus.
Uh, I think we said it tells us how strong the linear relationship is.
Then what is that? What measures the strength? What measures strength between the linear relationship strength between two variables?
Correlation. Correlation coefficient.
Yes. So basically, multiple R is the correlation coefficient. Okay. Maybe can you perform correlation here? Let's that is perform correlation and see if we'll get the same value. Okay. Let me do it here. So it is correlation cor of the first array, okay, comma, and the second array. So is it giving me the same value?
Yes.
Yes. So that is what? That is the multiple R basically is the correlation coefficient. Okay. It shows us how that is the strength of the linear relationship. Okay. Between what? Rainfall and umbrella cells. Okay. Then we have what we call R squared. Now R squared is the coefficient of determination. Okay. R squared is the one which measures that is the goodness of fit of our model. Okay. Like what percent of that is of our data was used to do what? To create that model. Okay. Meaning if we get this that is a value of 0.91, it means 91% of our data was used to create the model, or was used to what? To plot that is the regression, or was along the regression line. Okay, so basically that's what it means. Then for adjusted R squared, now this is also, it also measures the goodness of it. Okay, but for what? For more than one independent variable. Okay, why? Because we are calling it adjusted, because once that is, we now incorporate more than what? More than one variables, independent variables. Of course, it will bring a shift. Okay, or it will bring an adjustment. Okay, in the what? In the R squared, because in this case we'll be checking, or we'll be dealing on what? On that is with two independent variables. Okay, so that's why we call it adjusted R. Okay, maybe you can go and study more just for that is for your knowledge. Okay, you can go and research more about the adjusted R under multiple linear regression, because that we won't cover multiple regression. It is not within the scope of this topic, but it doesn't limit you to learn more. Okay, you can go and learn more about the same. Okay, the other thing is now the error term. What do you understand by the term, that is by this standard error? What is the standard error? What is standard error? Someone?
Let me try.
Yes.
I think it is. It represents maybe how far maybe the results
Mm-hmm.
may vary either upwards or downwards. That is plus or minus
Mm-hmm. Correct
that
for that
figure.
one. Uh-huh. Might vary.
So that means yeah, it might vary either upwards or downwards,
Mm-hmm.
but as far as that figure is concerned, not more than or less than that.
So which figure?
Yes.
Which figure? Like for example, if we have a standard deviation of positive 3.55, what does it mean? Of course, it shows us the that is the it's like
So I
more
mentioned
over.
that
Yeah.
anything.
Yes.
I think anything that tries anything you that we the result we get.
Mm-hmm.
Anything that deviates by that margin is acceptable.
Mm-hmm. Like in terms of residuals.
Can I try?
Yes.
I could say that between the prediction and the reality of the umbrella sword,
That
there
is
could be
between.
some errors
Yes.
on
That.
individual samples. So if we
Correct.
can see the standard deviation between those errors on the mean, that should be the standard error.
Correct. Well explained. Okay, like basically here we are trying basically standard that is the standard error tries to show us the standard deviation, okay, between the actual and the what and the predicted values. Okay, that is between the actual values of umbrella cells and the new predicted what variables. Okay, that's the standard error. Okay, and we usually say that the smaller the standard error, okay, the smaller the standard error, the more like significant our model is. Okay, it means like there is no big variation, okay, or there is no big deviation between our actual values and our predicted what values. Okay, so if we get zero or if we get a value closer to zero, the better. Why? Because it shows us like it can be also be used as a measure of the goodness of it. Okay, if we get a standard deviation which is small, then we can say what? Then we will say that our that is our we have a good that is our regression line is good fit. Okay, so basically that's what standard error mean. Okay, and that's why you can see our that is our r squared, that is the coefficient of determination. You can see it is a good value. Also you can see the standard error, it's also a good what, it's a good value. Okay, if the standard error we could have gotten a standard error value which is bigger, okay, than that is bigger or smaller, okay, than that is more small or more bigger, then of course we'll have that is our lower value. Okay, we would get a lower value for r squared. Okay, because these two move together. If we have a good value for r squared, so we will also have a good what? A good value for standard deviation. Okay, sorry, for standard error. That's why we are saying that that is the R squared, and standard deviation can be used to tell us the goodness of fit of what? Of our line. Okay. All right. Then what about observations? What about the observations?
Can we say that observation, these are the size of, this is the sample size that has participated in the
Correct.
regression?
Correct. Yes, of course. So observation is the sample size. So if you count here all these values, like for one variable, you will get what? You will get 24. Okay. So observation, basically, if we are dealing with the sample size, with sample data, it's the sample size. Okay. All right. Let's try and see what now the nodes tell us. Okay. Let's see what the nodes tell us. Okay, so we'll start here. So this, I will share this file with you. It gives you a step by step, okay, how you can do what, how you can run that is the regression. Okay, you can see the way we inserted our inputs. We came to labels. We came for us, we used the output range. Okay, and then we came to what, to the residuals. Okay, then now let's come to the interpretation. That is interpretation of the output. Okay, so this is our output which we got here. This is our output. You might find we have some difference, okay, in that is in some values, because of, I can remember there is a value here which I changed. Okay, in my data set, in my original data set, there is a value I changed here. Okay, so that's why you can see a very slight what, deviation, but the aim here is to get the what, the inference part of it. Okay. All right. Don't know. Joseph Munene, maybe you can mute on your side. Okay. Thank you. Thank you very much. Okay. Good. So now let's start with multiple R. Okay. So multiple R basically is the correlation coefficient. Okay. That measures the strength of the linear relationship between what? Between two variables. That's correct. We've talked about that. So the correlation coefficient can be any value between -1 and what? And 1. And its absolute value indicates relationship strength. The larger the absolute value, the stronger the what? The relationship. Remember we talked about that number line. I even drew like what value can we term as strong, what value can we term as weak. Okay, so for remember we said 1 means we have that is a positive 1, means we have a strong positive relationship, and in this case increase in one variable will trigger an increase in what, in the other, in the other variable. Okay, then we also have that is -1, where it means that is a strong negative relationship, and in this case we said now like decline in one variable will trigger maybe an increase in what, on the other variable. Okay, and then we said a value of 0 or close to 0 means that is we don't have any relationship between what, between the two variables. Okay, all right. Yes, we have a question. Yes, Aim.
Thank you. I would like to ask, since that you are showing that the correlation coefficient can change between -1 to 1, is it always from the calculation that you can make that we will find the minus 1 to 1. Or there could be some scenarios that it can get out from that. If that happens, how do we interpret that correlation coefficient?
Like, can you give maybe an illustration? Like, if this
Okay.
unchanged,
Let's say
mhm.
we have maybe two variables that are unrelated completely.
They are unrelated
Completely,
Okay,
the two variables.
okay,
And then when we try to model, when we try to apply linear regression,
mhm.
and we give a value closer to minus 1, no, closer to 0, or because, or it may change to minus something else,
Okay,
more
so
than minus 1 or plus 1.
okay, good. So if we have like that is two variables which are not correlated, okay, also the nature of the data depends, okay, because what if maybe I might be having to but okay, let me try and show you. Do I have really a good example? Like, okay, basically what I mean, if for example we have two variables which are not correlated, meaning if one has a pattern, maybe it's increasing, okay, and the other one it is not, like, it's not changing, okay, or what can I really say, like, basically what I can say here, like, if the values totally or if the two variables don't have that is any relationship, okay, then it will return a correlation value which is that is almost, okay, zero. It might be a negative or a positive value, but very much close to what? To zero. Okay, you might not get exactly zero, but what about if you get a correlation of 0.025? What that means, it means it's almost a zero value, okay, so meaning even if it is trying to portray a relationship, but that relationship is what? Insignificant. Like, for example, if we are trying to check maybe blood pressure, okay, blood pressure, and I want to use another variable which is not which does not influence blood pressure, okay, like for example we know age influences blood pressure, okay, obesity we know influences blood pressure, okay, smoking can also influence blood pressure, but that is very minimal. I want something, any factor which does not influence that is blood pressure.
The length,
Sorry.
length, length of the person cannot
Oh,
influence the
the
test.
height of the person.
Yes, that's it.
Okay, yes, like height of if you were to maybe to take some values between the length, that is the height of the person, and the that is comparing if blood pressure is influenced by that is length. So if in that case, or maybe blood pressure and the length of your hands, or blood pressure and the what length of your legs, okay, definitely for that case we don't have any correlation, okay. So what do you expect if you had a data set for blood pressure, okay, and data set for maybe your arm's length, okay, so definitely you'll get what? You'll get that is a small like a correlation of almost zero, okay. Why? Because at some time you might find someone with that is long arms have blood pressure. Also, at the same time, find someone with short, that is arm length, okay, or short arms, okay, as also high blood pressure, okay. So you can see that these two variables cannot do what, cannot correlate, okay. So in this case you might get a zero or a value very close to zero. It can be 0.002 or 0.01, okay. So for that value it's close to what, it's close to that is to zero, okay. Compared to a value like 0.45. I don't know if I'm clear.
Yes, sir, you are very clear. But I had experience. Let me share experience, maybe to you, that maybe people will prove. There was like a variable that I was like checking between the two. Then when I was analyzing, I get maybe, was it minus something related to 900 or something that when I did the literature, they said that the two are not correlated, even though that the result is out of -1 to 1 range. Yeah,
Okay.
that's the answer.
Wait,
And
for
when
that. Okay, I now got you. I now got you. I now got you. Like
yeah,
it's outside the range of -1
exactly,
and 1.
exactly. Yeah.
That's
And when
tricky.
even when I checked the scatter plot of that, I could see that it was following another function.
Yeah, so for that, of course, it cannot be correlated because if they were somehow correlated, okay, we could get a value between the range -1 and 1. And for my case, I could advise if you get any value which is outside those that range, maybe you might have to recheck on the maybe on your calculations. But I've never came across such that is a problem. But for covariance, yes, for covariance I can get that is a value which is even 1 million or -1,000. Okay. Okay, good. Let's continue. Okay, so then we have the r squared. Okay, so for r squared, it's also known as the coefficient of determination, which is used as an indicator of the goodness of fit. Okay, it is an indicator of goodness of fit. It shows how many points fall on the regression line. Okay, remember that is how many data points fall along what, or fall on the regression line. Like our value, we that is we got a value of that is 91%. Okay, meaning that that is our that is maybe we say that that is 91, that is our linear regression consumed, okay, of our linear or 91% of our data points were within what, were within the regression line, okay. Or we can say that 91% of our output, okay, can be explained by what, by the independent variable, okay. Like 91% of umbrella cells can be explained by what, by change in what, by change in the, or by the different values of the rainfall amount, okay. Okay, so we say that it is an indicator of goodness of fit. It shows how many points fall on the that is the points fall on the regression line. The r squared value is calculated from the total sum of squares, more precisely the sum of the square deviation, okay, of the original data from the mean. We have a very long that is formula for calculating r squared. Okay, formula for r squared. Okay, for r squared in regression. So we usually have this formula. Let me check. Okay, yes, this is the one of the formula, but let me show you the best formula. This is for the unadjusted. Yes, this one. You can see we have, that is the this is for the r on, this is for the what do we call the another formula for if you can remember, is it correlation, calculation for correlation. Okay, not correlation, yes, correlation, where correlation we know it is the covariance divided by what, divide by um, divide by standard deviation of the two variables. Okay, and this is the like the Pearson rank. Okay, but for that is r squared, it's basically given by this sum squared regression error divided by sum squared total error. Basically this is the formula. Okay, we have this formula, that is r squared equal to 1 minus this divided by this. Okay, this is majorly the formula for the that is for the standard sorry, for the r squared. Okay, that is coefficient of determination. Okay, so we've said that the r squared value is calculated from the total sum of squared. More precisely, it is the sum of the square deviation of the original data from the mean. In our example, we got a value which is 0.917. Okay, when it is rounded to two decimal values, where, oh, does it mean I, okay, yeah, here it is. Okay, so you can see this was our value. Okay, this was our value. So what does this value mean? Okay, so basically this value means that it means that um, of course, first of all, we've said this value is fairly good, though it's not good enough, but it's fairly good. Okay, and it means that 91% of our values fit the regression analysis model. Okay, 91% of our values fit the regression analysis model. Okay, or it was used to fit what, our regression, that is our regression line. That's why you can see it shows how many data points fall on the regression line. Okay, in other words, 91% of the dependent variables, okay, 91% of the dependent variables, y values, are explained by the what, by the independent variable x values. So basically we are saying that 91% of the umbrella cells data, okay, can be explained by the independent variable. Okay, so basically or generally, r squared of 95% is more considered as what, as a good fit. Okay, why? Because if we use this, it means our confidence, if we get a value of this, we it will be almost same to what, our confidence level. Okay, so if we get a value which is 95%, okay, or 0.95, we usually say that this that is the model, it's a good one. Okay, but of course our value is 91% or 0.9, okay, which it's fairly good. Okay, but for 95% it's better, of course, than that of 91%. Okay, all right. Then we have the unadjusted r squared. Okay, we have the unadjusted r squared. So for the unadjusted r squared, it is the r squared that is unadjusted for the number of the independent variable in the model. Okay, so in basically this it's used where we have what, where we have more than one independent variable. That's why we are saying it is the r square unadjusted for the number of independent variables, okay, in our model. You may want, or you will use it, you will use this value instead of r square for what, for multiple regression analysis. But if we are dealing with simple linear regression, it is advisable to use what? To use the r square value only. Why? Because we've not adjusted the r squared values for we have one independent variable. But if we had two, then we could have used the adjusted r squared. Okay, good. Then we have the other part, which is standard deviation. Oh, sorry, standard error. Okay, standard error. So, as I had told you, standard error is also good. That is another way of that is showing goodness of fit. Okay, or it's another goodness of fit measure. Okay, so it is another goodness of fit measure that shows the precision of your regression analysis. The smaller the number, the more certain you can be about your regression equation. Okay, so the smaller the number, the better the model. Okay, or that's why we are saying the smaller the number, the more certain you can be about your regression equation. Okay, while r squared represent the percentage of the dependent variables variance that is explained by the model, standard error, okay, is a measure that shows the average distance between the data points, okay, from the what, from the regression line. Okay, so it is showing us the distance between our data points and the what, from the regression line. Okay, that is the standard error. Then for observations, we said it is simply the what, the number of observations in your model. Okay, basically it's the n, the sample size. All right, okay, good. Now we will go to the ANOVA part. That is the second part, which is analysis of what? Analysis of variance. Okay, which is this part. Okay, good. Now let's start with DF. What is DF? What does
Degrees of freedom.
Okay, good. It is the degrees of freedom. What is degrees of freedom in statistics? And remember that is used only in sample data, where we are talking about the sample size. What do you understand by the degree of freedom?
I don't know. But let me try, sir. I could say that if you have any variables, then we have, meaning that as we remain with the degrees of freedom of n-1 to be able to decide.
Oh,
Maybe. you can infer anyway, I don't know. Kind of.
Of course, you've just said that is how we present that is degrees of freedom, because we know for a sample size we usually say we have n minus 1 degrees of freedom. Okay, but maybe to tell you that is the degree of freedom. It basically shows us that is the independent pieces. Okay, like like the number of independent what can I say values. Okay, that you can use maybe to do what, that you can use maybe in your analysis. Okay, like for example, that is for this example. Okay, we used what, we used a degree of degrees of freedom of what, of 23. Okay, so meaning now when calculating maybe our that is our analysis, like when we want to talk about the sum of squares, the mean square. Okay, instead of, like for example, when calculating the mean of the mean square, okay, we usually divide by n in most cases. Okay, and n is majorly for that is for the population. Okay, but for that is for any sample data, we usually now use n minus 1. Okay, meaning we are using that 23 values. Okay, excluding one value, just to make sure we use it as a sample data, even if we presume it's a sample data. But when we are talking about degrees of freedom, we can't actually assume. Okay, that's why it usually takes one that is value from the what, from the that is from the data, from the from the sample size, or from the size. Let me by the let check if we can have like a better explanation of that. Okay, degrees of freedom, meaning in statistics. So you can see degrees of freedom are the number of independent variables that can be estimated in a statistical analysis. Okay, that can be estimated in what, in statistical analysis, like the number of independent variables maybe we can use in what, in statistics. And just let me check another one. So degrees of freedom also refer to the maximum number of logical independent values, which may vary in the what, in the data sample. Let me try see another one. It represents how many values involved in what, in calculation. Okay, that is, represents how many values involved in calculation have the freedom to vary. Okay, you can see this one represents how many values involved in calculation have the freedom to vary. Okay, in some that is in sample mean, we know that when you estimate a sample, when you have a sample and estimate the mean, you have n minus 1 degrees of freedom, where n is the sample size. That is consequently for one sample t-test, using n minus 1 to calculate the okay. I don't really get that is a better value, that okay, like a better explanation for this. Okay, yeah, so basically that's what I could have explained. Like it measures maybe the number of variables, in this case the independent variables, which you can now use to maybe estimate or to do an estimation in what, in a statistical analysis. Like in this case for our regression, we used what, we used a total of 23 degrees of freedom, that is n, which is our observations minus 1, which is 24 minus 1, giving you 23. Okay, let's try and check what the notes here are telling us. So degrees of freedom, okay, that is df, is the number of degrees of freedom associated with the source of variance. Still, this complicates it. Maybe anyone who can explain it better in the class? Donald?
Hi, Abraham. No explanation from my side.
Okay, Jennifer? Maybe you have that is more insight on the that is on the definition of degrees of freedom. Jennifer?
Yes, sir.
Any maybe a better explanation of or layman's explanation on the degrees of freedom?
I don't know if I have much to say, but from what I have searched, they said it's just the values that have the freedom to vary in the data sample.
Yeah, like they have they can do what, like they are free, or they have freedom to vary. So in this
Yeah, yeah.
case we had 23, that is that is independent what, in count, that is 23 independent variables which can what, which have freedom to vary. Okay, all right, maybe we can take that as a food of thought, maybe to get, yes, Rebecca.
I see as another statement says that the idea that they are related closely to the idea that when you have a sample, not all values can vary independently. So it's not, I just found the idea that it's not only that all values can vary independently when we say they all vary,
Okay,
but not all can vary independently.
okay.
I I think that statement differs from the one my colleague said somehow.
I can see maybe we have different versions for the same. Okay, I don't know how. Maybe, but maybe we can check on that is on the same and see maybe what we have. Okay, if we can get maybe a better explanation of the same. Okay, then after that we have means, that is sum of squares. Okay, sum of squares. By the way, okay, yes, Jennifer, I can see your hand, it's up. Jennifer, maybe you are speaking on mute.
Yeah, so I was speaking on muted microphone.
Okay.
I was asking, is it always true that the degrees of freedom equals to the sample size minus one?
Sometimes it might vary. You might, I don't know if I'm the one forgetting, but there is some cases though back in campus we used n minus 2 or k minus 2, but I don't really know that is the exact that is the like when we use n minus 2 rather than n minus 1.
Because what I was saying, I'm just getting it from Investopedia.
Mm-hmm.
Yeah, that's what they are saying, that the degrees of freedom equals to the degrees of freedom are calculated by subtracting one from the number of items within the data sample. So I was wondering if it's always like this.
But most of cases is always n minus 1. Most of cases is
Oh,
always,
there.
yes,
Okay.
it's
I'm
always
just using this one. That's Investopedia.
okay. Yeah, I guess so. We have Rebecca. Yes, Rebecca.
Another part, the definition here says the specific formula for the degree of freedom can vary depending on the statistical tests or method being used.
That is,
So
if
it's not
maybe
always
you
like
are, yes, if you are doing a have test or if you are doing a t test,
we
uh,
test chi-squares, so
chi-square
it depends.
test.
Yes.
Yeah, it, because I can remember. That's why I'm saying there is. I don't know if it is in student t tests. It's long time ago when I used degrees of freedom. There is somewhere we were using n minus 2 instead of n minus 1. Okay, that's why for this I was not much sure if it's always n minus, but I know in most cases it is always n minus 1, but as you've said, it might vary from one test to another test. Okay, that is the F test, the chi-square test. We have the student t tests. They might differ. Okay, but what I know for F test, it's always n minus 1. Okay, all right, maybe we can continue. Then we have the sum of square. I was saying that that is let me show, I was in this also this. Yes, Jenga.
So these degrees of freedom, how do we use it in normal life? Like we data scientists, how do we use it? How can we use it?
Mostly that they are mostly used maybe when doing some statistics, like for example when you are trying to compare maybe a statistics like if we are, let me just show you, like for example here we have calculated something known as that is significant f. Okay, significant f, meaning we used what, meaning we used f statistic. Okay, f statistics. Okay, f statistics, maybe let me show you the formula. Okay, meaning we use this f statistics. Okay, in this f statistics as well, for us to come up with a value, we usually also assume what, we usually also assume degrees of freedom. We usually assumes a certain degrees of freedom. Don't know why it is that is it is still loading. Okay, that is for f test. Maybe you can go and search more of on the f test. Okay, that is for one tail and for two tailed. Okay, when you get this value, like when you're calculating this f test, okay, just to get a significant f or a value which you can compare with what, which you can compare with the p value. So remember, the p value is like a probability value. Okay, which tries to show you if your statistics is significant or it's not. Okay, so I'm just explaining how maybe it helps you. Like if you are now calculating something like this, because of course we'll need this significant f to do some inferences to see if that is our calculations, all these calculations where or our research is statistically significant, or if our model is reliable to use. Okay, so basically you will come now to use degrees freedom knowledge to calculate the f statistic value. Okay, whereby now you'll see that is once you get the f statistic value, you will now go to what we call f statistics, that is all our f statistic table. We have a statistics table, which is one. It's long time I used it. Okay, so we have a f statistic value, and you will come now to check maybe the significance f value. Okay, so we usually say whenever you get that is a significant f value, we usually compare it with what? With a p value. Okay, and a p-value, okay, it is like a probability which shows us, try to show us how our that is model is statistically significant, or how our model it's what? It's that is it is reliable. And for the p-value, it's always a value which is that is 5%, okay, or 0.05%. And they usually say that if your f statistic value is less than 5%, okay, then your model means it's statistically significant, or can be what? That is, your calculations are making statistical sense. Okay, and that also your results can be what? Can be reliable. Okay, but in case you get a f statistic value which is greater than 5%, okay, then it means your model it doesn't statistically make sense. Even though I guess the last year we had a debate, that is there was a debate which was going around, that is to do what? To like to remove that is the p-value as a measure of statistical significance, but I did not follow up and to know maybe where that is the argument went to, okay, or reached. Okay, so basically what I can tell you, that is degrees of freedom are majorly used when we are calculating these statistics. Okay, and these statistics, it is like for sure right now if I tell you that is if I start now telling you how to calculate this, okay, at some time I might that is because it's long time I used this. Okay, because this it's already calculated. For my case, I usually just go to the significant f, all to the end result. Okay, because Excel does it for me, so the back calculations, all the formulas involved to this, I might it might I might be lying to you. Yes, aim.
Okay, what I could support on what you are, just to emphasize what you are telling, the degrees of freedom is something very important, even though that we are not entering into a lot of explanation to it, but their usage, especially for in this built-in algorithm, they use their mathematics as if we like the way we do when we do hypothesis testing. In that case, depending on the test that we are using to be able to test the null hypothesis and the alternative hypothesis, we could have the p-value. And if you look at the table, you cannot be able to find the p-value without knowing the degrees of freedom.
Of course.
So the degrees of freedom is very important. Once you know, the way to calculate the degrees of freedom on a particular test, you can now know how to read the table to be able to find the p-value that will guide you either to prove or to disapprove
To
the
disapprove.
null hypothesis.
Yeah, that is either to accept or fail to accept.
Exactly. Yeah.
That is the null hypothesis. Yeah, so maybe for this, I can just send you to do more, that is research on how we perform this, that is tests. Okay, you can go and maybe research on this because, of course, for you to calculate this, you must use that is degrees of freedom. Okay, that's also maybe I'll just send you and maybe learn about that. Okay, but for my, that is for this analysis, significant f, it's our what, it's our target, this calculated value. Okay, this calculated value is what we are targeting. Then we also have sum of squares. Okay, so sum of squares, that is for what, for residual, can also be used to check if our model, it's a good model. Okay, so the smaller this value, okay, compared to total, that is to the total sum of squared. Okay, that is, the smaller this value is in comparison to the that is the total residuals, or to the total sum of squares. Okay, shows that we have like our model, it's also good. So sum of squares, we have ss, that is ss is the sum of squares, and we've said that the smaller the residual, okay, compared to the total sum of squares, okay, the better the model, it fits what, it fits the data. Okay, then we have the mean square, then we have f statistics, and you can see, as aim has said, that is, f statistics is majorly used for f tests, more so if we have some hypothesis testing. Okay, so like f test for null hypothesis, it is used to test overall significance of the model, if the model is significant or it's not significant. Remember that that is for null hypothesis always states that there exists a significance, maybe difference between maybe the two statements you are trying to do what, to hypothesize. Then for the alternative hypothesis tries to show that is the other way. Okay, it tries to show that there is no significant difference. Okay, so we have significance f, which is a p-value of f. So significance f, now we usually use this value, that is significant f, to compare it with the p-value, which is of 5%. Okay, whenever we have that is a value, or our significant f value is less than 5%, then we usually say that all our calculations, or maybe we can say that our model is okay, or it's reliable, or it is statistical significant. Okay, so like for example, the ANOVA part is rarely used for simple what? For simple linear regression, of course, because mostly we use ANOVA when we are trying to see, like, to do some analysis variance between what? More independent variables. Okay, that's why we say that is we rarely use it for simple linear regression, but for multiple linear regression, it's very, very useful. Okay, so in Excel, but you should definitely have a close look at the component. Okay, so the significant F value gives an idea of how reliable or statistically significant your results are. Okay, so if the significance F is less than a p-value of it's less than the p-value, or it's less than 0.05, okay, then your model is what is okay. But if the significant F value is greater than 0.5, then you would probably choose what? Another independent variable. Okay? Why? Because it will mean that that is your variables does not bring that statistical. It's not statistical significant. Okay? So basically, it will show that. Okay? So for that is for the ANOVA, all the analysis of variance, the most important value to check is the what? The significance F. Okay? Or sometimes you can check what? The sum of square, the residual sum of square. So under ANOVA, these are the two major what? Two major indicators of how our models are performing. Okay, then the last part, it's now the analysis output. Okay, the analysis output. So for the analysis that is, sorry, for the coefficient outputs, we are we will measure that is our discussion on the coefficients now, because these are the coefficients which we will use to build what? To build our model. Okay, so you can see these coefficients exactly looks as what? As these coefficients we got for the first method. Okay, so you can see here we have what? Here we have that is the same values. We have the same values. So meaning our both methods gave us the same output. Okay, good. So maybe what does it mean here? Okay, we have a question. Yes, I can see him. You've raised your hand.
Yes, sir. I would like, it is very important to know how do we set the two hypotheses for that test. It's very important for that test.
Okay, so for like
Yeah, sure.
sorry?
The null hypothesis and the alternative.
The good thing, we still have that topic. That's the good thing. Okay, I will show you how we usually set that is an hypothesis, that is a null hypothesis, and an alternative hypothesis. The good thing, if you set the null hypothesis, it's very it's like it will do what? It will definitely give us the alternative, because it will always do what? It will always be the opposite of the null hypothesis. Like for example, if maybe we are to do a null hypothesis, okay, or an hypothesis testing for this statement, okay, that is all statistics students, okay, have intelligent quotients, or they have IQ which is above 90%, okay, or intelligent quotient of maybe which is above 100, okay. All right, then the that is a motor, maybe is it motorbike, maybe do we say riders? Okay, let's say like we are trying to compare the IQ of statistics students, okay, and that of that is motorbike, let's say riders. Okay, so in this case, that will be what? That is our null hypothesis will be there exists, okay, there is a difference, okay, between the IQ of statistics students and that is the motorbike riders. Okay, there exists there is a significant difference between the IQ for that is for the statistics students and that of motorbike riders. Okay, now the null hypothesis will be there is no that is significant difference, okay, between that. Why is maybe alternative hypothesis saying that? What if maybe those motorbike riders, okay, they were once statistics students. Maybe they were they went to college, they did statistics, but that was what they are like. That is one of their maybe ways of that is getting a daily bread. Okay, so in this case we are trying to compare, like, to test our hypothesis. That is our just an assumption. Okay, so we are trying to see how true it is when it comes to hypothesis testing. That's okay, aim, or maybe aim has dropped. Okay, good. You can see someone is requesting. Yeah, so good. I hope aim that was clear.
I lost internet a bit, but yeah, it's clear, sir.
Okay. All right. Now let's go to the that is the analysis output. That is the coefficient output. So basically, this is what this was our coefficients. We got our coefficients here. So, and you can see they are the same as that of that is yesterday's method. Okay, good. Then let's come to that is the prediction. So what the model here did, it took the same pattern of rainfall amount. Okay, it took the same pattern of rainfall amount and predicted the umbrella cells maybe which they it could have done. That is the umbrella cells which we might sell. Okay, so this is what the model did. It took the same that is values of rainfall amount and did what? And that is projected this. Maybe we can try the same just to validate. I'm just going to use that is the forecast, the linear forecast method. I need the x value, okay, and I will need the y that is values, and I will need what? That is the y and the x. Sorry, it should be first the y's. Let me redo it. The y's, okay, these are the y's. Then the non-x's, okay, and you can see we are getting the same value as this one. You can see this is the same value we are getting here, meaning they assumed the same what? The same rainfall pattern. Of course, we can try and fill all in that. Can still fill in everything and then drag it down. Okay, so you can see we are getting the same values. Whatever is here, let's just check if that's true. Whatever it's here, so is this equal to this? Equal to this? Yes, it's true. So you can see the values are the same, meaning that's the method they used. Whenever you see false, maybe it's a difference in what? The decimal values. Okay, maybe it's the difference, but majority it's true. That is just a check. That is to check if that's true. Okay, then remember what we said about residuals. How do we calculate our residuals? Here it's the residuals. Okay, remember what we said, that is how we calculate the residuals. Okay, so we said we take the that is the actual minus what? Let me just paste the actuals here. We said it's the actual minus the predicted, or we said it's the predicted minus the actual. Should be the actual minus the predicted. So the residuals, we said it is equal to the actuals minus the predicted. Okay, and see if we'll get the same values as we got here. So yes, you can see we are getting the same values. These are the same values. Okay, maybe we can try and prove that if this is equal to this. Okay, it's showing me false, and I know why. It is showing me false because of maybe some decimal spaces. Okay, maybe the number of decimal spaces we have here. So, but if you check closely, it is what? It is the same value. Okay. Yes. So this is how we got what? We got the residuals. Any question on how we got the predicted values and the residuals? Any question? Okay, good. So maybe I will beg to stop here for today. Okay.